Our next speaker is not Judy Cohen. It's
Not Judy Cohen.
Heather Morrison. Heather Morrison. Heather Morrison will be speaking on behalf also of Ken Freeman. And they're going to talk about disk or Lyra stars.
As soon as I can get this attached. Oh, that's there. Try it again. Yeah. Okay. Put it in the pocket. Okay, I want to say something for myself before I say anything for Ken. Paul and I turned up at Santa Barbara Street in January 1989. Wet behind the ears doesn't even begin to describe it, right? We were sort of naive. You were very kind to us, George, and I wanted to thank you for that and your support, but also for the joy that you brought to our lives with all those jokes and bets and crazy things that we did. So thank you for that. Yeah, okay, so I'm going to talk about a real puzzle, which is a cool thing to be able to talk about. Yu Chen Lin did the heavy lifting on this thing, an honours student at ANU, working on disk Lyra stars. So what are these things? So back in 1959, George first showed that right, I can do this. The low delta S, which means metal rich, okay, field RR-AB RR-Lyra stars have short periods. They're not concentrated to the bulge the way the halo should be. They have velocity similar to the sun, and they have a low velocity dispersion, which all sounds like the disk, right? Tom Kinman also showed that they were closer to the galactic plane than a sample of RRCs with similar periods. George actually came out and associated them with the disk a few years later. And as the next slide will show very nicely, but as Andy Layden actually pointed out, I think in his thesis work in the 90s, thank you. These metal-rich field RR-Lyra stars have shorter periods than the disk globular cluster RR-Lyras. So this comes from this very nice paper by Chadid, Chris and George. And we have metallicity, spectroscopic, beautiful spectroscopic metallicities against period for a group of field RR-Lyras, the blue ones being, being the metal core thing, divided fairly arbitrary at -1. You know, it doesn't really matter exactly where you do it. These are the metal rich ones. And the green things are the globular cluster RR-Lyra stars. Right, got it out. And as you can see, they have much shorter periods. And I think this paper just said, I mean, you said it beautifully, you know, but I mean, you know, command of English was just lovely, but, you know, there wasn't a real explanation for that I could see. So why am I getting so excited about the whole idea that there are RR-Lyra stars that belong to the disk? Well, how do you know the age of an RR-Lyra star? Unfortunately, we don't have masses yet, so we can't do it directly, right? But what we can do is measure the ages of the globular clusters they live in. And every single cluster that does contain an RR-Lyra, okay, is older than 10 gig years. So as far as we know, RR-Lyras are significantly old stars. Now there are two disks, okay, and I'm not going to go into a lot of time about the differences, apart from one presumably formed, you know, when something came in about 10 gig years ago, okay, is the thick disk, okay. So if these RR-Lyras are part of the thick disk, there's no biggie, Okay, there's nothing that we have to explain age-wise, right? But if they're part of the thin disk, which is not only younger, but has a very nicely constrained age these days from white dwarf cooling ages in particular, okay, then we have, and this might sound familiar to those of us who are old enough to remember when H0 gave us, how was it? The globular clusters were older than the age of the universe, if you believe some versions of H0. So we have a similar thing, okay? We would have members of a population that were significantly older than the population should be, okay? So that's the sort of puzzle behind why I'm talking about this today. So John Martin and I, back in '98, actually took a sample of about 130 RLRs, which was originally put together by Tom Kinman, had exquisite photometry, and we got velocities and calculated UVWs, stellar motions in the 3 components in the galaxy. Okay, and we once again found that that there were stars that looked as if they were disk stars. But we were using ground-based almost, either Hipparcos or ground-based proper motions, okay? And here we have, once again, metallicity against the rotational velocity, okay? So, and that's, I think, the local standard of rest velocity. So if you're up here, you're going round at of order 200 kilometers a second. If you're a true halo thing, you know, that's 0 velocity, you know, galactic center, okay? And once again, you see that we have a whole lot of stars. Well, I wouldn't say a whole lot, especially in the, after the last talk, right? But we have significant numbers of stars which are definitely rotating and do not have halo kinematics, particularly in this range, okay? We chose to draw the line at -0.9, but I'm not going to make a big fuss about it. Okay, I should say that we had proper motion errors of about 3 milliarc seconds a year. Gaia, for this velocity range, has proper motion errors of about 0.05 milliarc seconds a year, okay? When you add the fact that you've also got slightly better distances out of Gaia parallaxes, which I'll talk about in a minute, we're gaining about an order of magnitude by actually adding in Gaia DR2 data, okay? And in fact, there are 3 groups who've been working on doing this in slightly different ways. And I don't know how to pronounce his name, so I'll say Prudil et al. And apologize. I think he's actually online at the moment if I'm getting it wrong. And Iorio and Blocherov. Okay. The real difference between those 2 groups is that this one. Okay. Prudil et al. Had spectroscopic abundances, and these guys used a less accurate method of obtaining abundances based on the periods and things like that. Okay, all 3 of us were working on trying to really understand, do these things belong to the thin or the thick disk? And first of all, a sample of order 300 RLR stars, ABs, which are the ones we want, our fundamental mode. They're all within 4 kiloparsec of the sun. They all have spectroscopic abundances, good radial velocities, and Gaia parallaxes and proper motion. Okay. There's a wrinkle here about using Gaia data, which I independently rediscovered with a student in the very early days of, it was probably about 20, yeah, anyway, which is that you don't just take the parallax and do 1 on pi, because that gives you a biased answer. Okay, so you need a proper Bayesian analysis in order to work this out. And Corin Baylor-Jones very kindly made these available with a reasonably good prior for what we want, okay? So I think the next slide actually shows us the comparison of the, yeah, okay. So the photometric distance is the distance that Martin and Morrison and Kinman and, all of us who used to use RLRs before we had Gaia used. It was a good photometric distance. And this is the Bayesian Gaia distance. And as you can see, the one-to-one line looks pretty good. It turns out we chose to use, look, we've even got the equation for it. Yeah. Okay, and we had metallicities from spectra that I took on the Palomar. Yeah, exactly. They were a lot of long nights watching RLRs go up and down. Yeah, anyway, so we chose to use the Bayesian distances because they agreed with the photometric distances but had a smaller scatter. Okay, so we really have a nice data set to work with now. So now just going back to, you have to point it? No? Yeah, here. We got the FNH values from a compilation from Dambas et al., which is basically Andy Layden data. Andy's thesis has been very valuable to a lot of people. Okay, so what are we going to do with all this stuff? We're going to look at metallicity against the 3 components in the galaxy, okay, for this very local sample. And then what we did was basically, I should say that remember that RLRs are getting smaller and bigger all the time. So actually getting a velocity of an RLR is like Alice in Wonderland trying to play croquet with the flamingo, and the flamingos used to get up and walk away and all that sort of thing. So what we actually did was we required that our velocities and the Prudel et al. Velocities agreed within 15 kilometers a second, okay, which is a small number with respect to the, 3 minutes. Okay, I better speed up. Okay, so this is a Tourmaret diagram which shows the rotational velocity, okay, with the sun or the LSR there, okay, and 0 rotation there, okay, and this is the dispersion in the other 2 components. And what we find is that the metal-rich ones, which are the red ones here, are all clustered in both velocity dispersion and in rotational velocity near the sun. Okay. So this is the radial velocity versus metallicity, so radial outward in the galaxy. And Ken has very kindly put the velocity dispersions of the 3 components, thin disk and the metallicity ranges for thin disk, more than -0.5 and so on there. So I'll just take you through these quickly. The rotational velocity, once again, you can see that the metal-rich ones are really going around pretty fast. And you can also see here, there's a pretty tight concentration right up there, okay? And the Z velocity, the vertical velocity, and once again, very tight Z component as you would expect if it was confined to the plane. Okay, so now we get a summary of the thin disk star kinematics, non-variable and thick disk. They come from the Geneva-Copenhagen survey, and ask me about that later. And let's just look at Z because it's nice and clear here that the non-variable metal-rich ones and the RLRs have a nice low thing. These numbers are very similar. And the somewhat more metal-rich ones look more like the thick disk. So, okay. Alphas, we'd like to try and get a handle on the alpha abundance. This is what the non-variables look like. And once again, the thin disk has low alphas. The thick disk is sort of intermediate, and the halo has quite high alpha to ion. And this is hard work, and I think this comes from the Eshel data again, that we get, oh no, sorry, it's someone else's data, okay? But once again, we find low alpha to ion for those metal-rich RLRs, okay? So, summary. There really is a thin disk component in these metal-rich RLR stars. both the kinematics and the alpha to ion, okay, are telling us the same thing. And they're really, I mean, those kinematics are really tight. Okay, so we've got about a 1 to 2 gig a year gap between the ages, the minimum age of an Arillary and the oldest stars in the thin disk. Okay, so what's going on here? And at this point, I should just summarize the results of the other two people. Prudel et al. Had basically the same result, but claimed nevertheless that the Arillaries, all of them were in the thick disk, in the tails, okay? Bolokarov et al., Bolokarov and his student claimed that they were in the thin disk. And I'm not sure went into a lot of interpretation about why. So this idea, it uses radial migration, which I really don't have a lot of time to explain, except that you don't have to conserve angular momentum. Okay, so if you take an inner galaxy Arillary from the bulge, say, okay, where there are a large number of the high metallicity ones, right, and it's on a near circular orbit, you can basically magically transfer it, only it's not magic, out to the solar neighborhood, where it would still have disk kinematics, which is what it had where it lasted. So this is a way of sort of getting around this real problem with the ages, to say that they weren't born here. Okay, they were born earlier in the center of the galaxy where things got going earlier. Okay. The other question, though, is that if they did come from the inner galaxy, why don't we find things with metallicities higher than 0? Because they go up to about plus 0.5 in there. So that's a bit of a worry. And so, you know, we're leaving you here with just possible explanations about what's going on here. But personally, I think this is an intriguing idea. Okay.
Thank you.
Thank you.
We have time for 1 or 2 quick questions.
I have a comment. I think that there was a paper back in the 70s, Kraft and Munson, who suggested that what you need to make an Arillary is to get it in the right mass spectrum.
Yep.
Both.
Oh, was this the term Kraft and? Yeah.
So it was a suggested mechanism that you would make a few stars.
Yeah.
The stochastic tail of mass loss from the top of the giant branch would land a few stars into where you want.
Half a solar mass of mass loss. Yeah, it sounded, you know, they certainly were in the extreme tail. But yeah, thanks for pointing that out.
One more quick question.
So we know that, so we have seen evidence of radial migration from other populations of stars. Is there any way that you could calculate, you know, what are the fraction of stars that radially migrate and apply that to the Arillary stars? I think we have a pretty good census of Arillary stars in the bulge from oval, and then say, okay, if X% of stars radially migrate, and we have, you know, we're assuming, you know, some completeness for the Arillary from the bulge. Does that correspond to the fraction? You know,
Yeah, that's worth looking into. Thank you.
Oh, that's what you're doing now.
Yeah, no, but I will be.
Yeah, that would be interesting to see if that.
Yeah, I'm not familiar enough with the constraints on radial migration, but I'll look into them. Yeah.
I fear we have to move on. Let's thank Heather again.